When you build out a web API, there are a tremendous number of decisions that have to be made about how you want the API to function. Over the years, I've built out quite a few production APIs and have gathered some tips and best practices I'd like to share with you. My hope is to give you some guidance and point you in the right direction if you're currently designing a RESTful web API. Before we get to the tips, we should note a few things here. The first is, we're going to be talking about tips for RESTful-ish web APIs. There are different approaches to building APIs, such as REST, SOAP, RPC, and GraphQL. They all have pros and cons, and I'd encourage you to gain a little familiarity with them to round out your understanding on the topic. The two most common you're going to come across at this point in time are REST and GraphQL. Our focus in this video will be REST. The REST architectural approach to designing web services was proposed by Roy Fielding in 2000. I'm choosing to cover it over the others, not only because it's the approach I've used to successfully build many of my production applications, but also it is still widely used today, and you're likely to come across it in your career if you're building any applications on the web. Note, you may have caught that I said RESTful-ish earlier. I added the ish because in practice most production APIs simply don't follow Fielding's RESTful architecture exactly as he envisioned it. If you want to dive deeper into the technicality of REST, I've included links to Fielding's work and to Leonard Richardson's subsequent work on a maturity model for web APIs. Okay, with that out of the way, let's jump into the 11 tips for designing an awesome RESTful API. Number 1, naming conventions. You should avoid using verbs for your endpoints and instead use the plural version of nouns that describe the resources you are managing. Do this in combination with the correct HTTP method for the action that you're trying to take. For example, if you were managing a collection of users, a good name for an endpoint would be v1 users. Then you could retrieve all the users with a GET request to v1 users, retrieve a specific user with a GET request to v1 user 5, update a specific user with a patch request to v1 users 4, and delete a specific user with a delete request to v1 users 9. This is opposed to having verb endpoints like v1 get users, v1 get user, and v1 update username. At first sight, the verb-based approach may seem like a good idea. It can offer you granular control over updates in your controller methods, for example. However, the verb-based approach quickly balloons, increases the surface area of the API, and calls for a lot of duplicated code. This not only becomes hard for you to manage, but also makes it difficult for consumers of your API to know what endpoints they need to hit to make specific changes. Essentially, this ultimately makes your API less intuitive. Number 2, avoid thinking of endpoints as a one-to-one mapping of your database tables. This is probably the most common mistake I see in API design when folks first get started. New backend engineers often think an API should simply implement all the CRUD operations for every table in the database. So they create an endpoint for each table and then go to work implementing the get, post, patch, and delete version of those endpoints. This will likely result in a suboptimal API design that is awkward and cumbersome to interact with, especially as data models get more complex. Also, the API ends up being too tightly coupled with the database structure, which makes it harder to change things without breaking the clients that are consuming it. Instead of thinking of a one-to-one mapping between endpoints and your database tables, think in terms of the workflows the clients are consuming the application are going to need. Then think about the resources needed for those workflows, the nouns that describe those resources, and the specifics of the relationships between them. With this approach, you'll likely end up with some routes that are simple CRUD mappings on top of database tables. But you will also end up with endpoints that are abstractions over the internal database structure. This will improve the usability of your API for your consumers. If this all sounds a little too abstract, let's take a look at an example. Imagine an e-commerce application where a product has variations, like a t-shirt with different colors and sizes. The database might model this with a series of tables, say a products, product options, product variants, and product variant options tables. For the client to create a new product, they wouldn't want to make multiple post requests to all of these tables. A better approach would be for the client to make a single post request to the V1 products endpoint, and the controller and service responsible for handling that request should deal with populating all those internal tables appropriately. In this example, the surface area of the API and the database tables are not one-to-one. If you just built CRUD operations on top of your DB tables, you would have missed the real point of the add product workflow and made it much more difficult for your client to create a product. Number 3, use DTOs. DTO stands for Data Transfer Objects. They help us define the shape of the data that comes into and goes out of the API. The main value DTOs provide is that they allow you to explicitly specify the contract that the API has with its client apps. This makes it clear what is expected and helps decouple the internals of the API from the client. The exact way you implement these can vary. The APIs I build often implement create, update, view, and view extended DTOs. For example, there will be a create user DTO that specifies the contract for making post requests to the user's input, an update user DTO that specifies the contract for patch requests to the user's endpoint, and often 2 DTOs for returning data, a view user DTO and a view user extended DTO. As a side note here, the reason I often have both an extended and a non-extended version of the view DTO is that the extended version will include nested properties for relationships where the non-extended version will not. I won't necessarily have an extended version for every resource in the API, rather, I'll only include it for the ones that I deem it to make sense. But the reason I do this is because when you get all items in a collection, you typically don't want to return the nested related entities. However, when you retrieve a specific item, you often do want to have the related nested entities. For example, imagine a case where an admin user of an e-commerce site wants to retrieve a list of active shopping carts. When getting this collection, you probably wouldn't want to also retrieve each cart's items. However, when you retrieve a single cart, it probably would make sense to nest the cart's items. In this example, a GET request to view the first 250 carts would adhere to the view cart DTO contract, while a GET request to view a specific cart will return a view cart extended DTO that includes the cart's items. Note, returning objects with nested related entities is one of the areas people will disagree on. Some people argue you shouldn't return these nested properties directly, but that you should return a list of links to where they can be found. As with many items in software engineering, things are quite a bit nuanced here, and you'll get better over time at choosing to include nested items or not. I'd recommend you go check out some popular APIs and look at the examples of how and when they return nested resources. Number 4, always perform validation on the server. Using a word like always tends to be frowned upon as it sets a rigid tone and discourages thought and healthy debate. While I typically agree with that, I'll go out on a limb and make an exception here. You should always perform data validation on the server. Don't rely only on front-end validation. There's simply no guarantee that a request your API receives has gone through client validation. And failure to validate on the server can not only cause unexpected behavior, but also lead to data corruption of your persisted data. A tip for those building their APIs in JavaScript, your DTOs can come in handy here. There's an npm package titled Class Validator that allows you to expand your DTOs with validation logic using decorators. I love this approach and have come to use it in just about all of my APIs. Number 5, accept and return decimal numbers as a string. It is common for APIs nowadays to accept and respond with JSON data. When you are dealing with integers, it's fine to return them as numbers in JSON. However, when you are dealing with numbers that have decimal parts, the API should accept and return them as strings. For example, if a user wants to set the hours billed for a project to 10.25 hours, have them submit a string of 10.25. Similarly, if the price of an item is $9.99, the API should return a string of $9.99 to the user. However, if the user wants to set a field that is persisted as an integer, that is a field where you don't need the decimal places, they should submit the value as a number, and you should return the quantity as a number. An example might be the quantity of shirts you have in stock. Doesn't make sense to say that you have 10.2 shirts in stock, so you choose to store it as an integer, and you would accept and return the quantity as a number. Now, the reason we want to wrap decimals in strings is that different languages have different data types for numeric values with decimals, such as float, double, decimal, etc. Those different data types offer different levels of precision. Providing the decimal values from your API as a string makes it clear to the client what the value is supposed to be and offers them the flexibility to parse the string into the data type of their choice in their language. Note, some folks make an exception here for currency values and default to representing them as integers and cents. So $9.99 would become 999 cents. I personally don't like doing this because I prefer the consistency of knowing that all decimal values will be strings, rather than having to remember that currency values are integers and cents and all other decimal values are strings. But you may prefer to make this exception, and that's perfectly fine. Number 6. When possible, work and store dates in UTC. I've been programming for around a decade, and I've come to the conclusion that quite possibly the hardest thing any programmer has to do is deal with dates and times accurately. If you don't believe me, just watch the computer file video, The Problem with Time and Time Zones. I've included a link in the description below. Trust me, it's a good one. Honestly, I assumed that by now I'd have this practice down, but it is way more complicated and nuanced than you initially think. Right off the bat, dates are relative to their frame of reference. There's the time zone of the client, the time zone of the web server, and the time zone of the database server, just to name a few. This can cause you to bang your head off the wall. I was recently on a call with a friend that was explaining to me a time zone offset bug he found in his application while he was traveling and just happened to be using the application from a different time zone. I don't think this is what Einstein was referring to in general relativity, but I'm beginning to be convinced it's about as complicated. The only advice I can give you here is to reduce the number of variables when possible. You can do this by setting your web server's time zone to UTC, your database server's time zone to UTC, and storing your dates in UTC. Then learn the ins and outs of a widely used and trusted datetime package for your language of choice. For the JavaScript land that I live in, Luxon is my package of choice here. Number 7, use versioning. You might have noticed by now that the endpoints I keep referencing are prepended with a v1. This is how I prefer to implement versioning in my APIs. As the version goes up, that would change to a v2. I'll keep this one short. Just know that using versioning from the beginning will give you the flexibility to introduce changes without destroying the clients that are consuming your endpoints. This isn't going to solve all your problems magically, but it will give you a little added flexibility, and that's worth a lot when you're designing APIs. Number 8, limit endpoint nesting to 2 levels. Unless you have a really strong argument, I'd avoid endpoints that are nested beyond 2 levels. Deep nesting does more harm than result in long URLs. It further tightens the coupling in your application, making any design shifts and changes hard to pull off down the road. As an example, an endpoint to get all customer users of v1 customers 1 users is reasonable. Here you have 2 resources, customers and users. On the other hand, I'd avoid having something like v1 customers 1 users 5 orders to retrieve all the users' orders. Instead of dealing with those 3 resource levels, I'd opt to get a user's orders from v1 users 5 orders. This isn't to say that you should never ever have more than 2 levels, but rather, seeing deeply nested endpoints should trigger you to pause for consideration and think more critically about your design before moving forward. Number 9, think about the relationships between your entities in detail. Designing routes gets the most complicated when you are dealing with entities that have relationships. The details of a relationship can alter the design of your API greatly. And I don't just mean the basics of whether the relationship is a one-to-one, one-to-many, or many-to-many. You need to go a level deeper here. For example, the API design required for working with entities that have a one-to-many relationship will differ depending on the specific requirements of that relationship. You can see this by considering 3 scenarios where the one-to-many relationship has different requirements. Let's first imagine a relationship between account and comment. Here, an account can have 0 or more comments, and a comment must belong to only one account. In this example, assigning a comment to a different account doesn't make sense, as the comment was meant for the account that it was added to. Also, if you were to delete an account, it would most likely make sense to delete all of its comments, as they would no longer be of any use in the system. Now, let's take a look at a slightly different one-to-many relationship, maybe between, say, organization and account. Here, an organization can have 0 or more accounts, and an account must belong to only one organization. However, a difference here is that an account can change organizations. I don't know, imagine one organization purchasing an account from another. Here, the API needs to handle the assignment of an account to another organization. That's something our comment example didn't have to account for. Also, our strategy for what we do to accounts when an organization is deleted isn't as clear-cut here. We'd have to really think through what should happen to its accounts. Lastly, let's look at the example of a one-to-many between, say, a team and a player. Here, a team can have 0 or more players, and a player can belong to 0 or 1 team. You can imagine a player getting cut from a team, then sits on the bench for some time, and then gets signed by a new team. You need endpoints for assigning and removing players from a team. And in this scenario, deleting a team almost certainly shouldn't just delete all the players. The point I'm trying to make here is that you need to think deeper about the requirements your application needs and the impacts those requirements have on the relationship between your entities, and in turn, the design of your API endpoints. All 3 of these were one-to-many relationships, but digging in showed they would require different API designs to support their requirements. Number 10. Find all routes should require pagination by default. Find all routes are unique in that they can quickly run into the problem of not scaling very well. This is because they return a collection of entities whose length can vary. Asking for all of an account's orders could return no orders, or it could return 1,000,000 orders. This unknown can cause catastrophic failure of the client and the server. While you may think you have intuition on what collections will become large, things do often change, and it isn't always obvious what collections will explode. This unpredictability is why I favor required pagination by default. That is, the API forces clients to use pagination either by requiring pagination query params or setting defaults when none are present. Notice the distinction between required and optional pagination. You could make pagination optional, and this is better than not having it at all. But you still run the risk of a client requesting everything and the server trying to return everything, resulting in a crash. You also run the risk of breaking clients when you realize that you have to switch from an optional to required pagination to stop those ridiculous give me everything requests from coming in the first place. Now, requiring pagination from the start will not only avoid those overly large requests, but it's also going to protect your clients from having to do a refactor once you do make pagination required. Unless you have a really good reason to believe the collection will not grow beyond a certain point, you should require pagination. In this video, we looked at 11 tips that could help you build better APIs. If you found the video helpful, please subscribe and like the video to help others find this content. FullStackFluent is a new channel focused on taking you from blank slate to production. Because we are so new, your actions carry more weight and have a huge impact on us. Thank you for the help, and thank you for watching. See you soon.